Welcome back to the next video, everybody. Today's video is the first video of chapter 6 of my notes, and this chapter will be covering the Langlands-Tunnell theorem and its applications to the proof of Fermat's last theorem. Setup and references. This chapter is going to be covering the skeleton of the proof of Langlands-Tunnell and also a major consequence needed for the proof of semi-stable modularity. I will refer you to Cornell, Silverman, Stevens, CSS, chapter 6 throughout the entirety of this chapter. And then the original papers to look at would be Langlands base change for GL2, which I'll call LBC if I refer to it again, and Tunnell-Artin's conjecture for representations of octahedral type. Okay, so let's think back for a second. If you recall in the overview of the proof of modularity, the following theorem, which I'll call Theorem 1, was used. Let E over Q be an elliptic curve, and let rho bar EP from GQ to GL2 of F sub P be the representation corresponding to the natural action of GQ on the P torsion of E of Q bar. So this is just the mod P representation attached to the elliptic curve, or the residual mod P representation, if you like. Now, suppose P is 3, and let's suppose this representation, rho bar E3, is irreducible. Then it turns out rho bar E3 is modular. Okay, so in other words, under the above assumptions, there's a weight 2 new form F with Fourier coefficients A sub n and a prime lambda in the algebraic closure of Q living above 3, such that AQ is equivalent to the trace of rho bar E3 on Frobenius set Q mod lambda for almost all primes Q. This is one way of thinking about modularity. It's quite a technical, detailed way, but go back and watch the videos on the overview of the proof of Fermat's last theorem if you haven't seen those yet to see what I'm talking about here. And so our first goal of the chapter is a meager one. We would like to see how Theorem 1 follows from the so-called Langlands-Tunnell theorem, which was a theorem known prior to the proof of Fermat's last theorem. Well, to do that, I'm going to have to tell you what Langlands-Tunnell is, right? So what's that? I'll give you two different statements of it. And one of the other goals of this chapter will be to connect those two statements with each other and see that one implies the other. But first, some definitions. Group G is solvable if there's a filtration. 1 equals G0. G0 is normal in G1. G1 is normal in G2, and so on, all the way up to Gn minus 1 is normal in Gn, and Gn just equals G of subgroups. And all I want to do is I want to require that the successive quotients are abelian for all I. So G sub I plus 1 mod G sub I should be abelian for all I. Okay, that's what a solvable group is. Okay, so for example, abelian groups are solvable. And recall that the complex projective linear group PGL2 of C is just GL2 of C. So that's 2 by 2 matrices with complex entries that are invertible mod the center, Z of C. What's the center? In this case, it's the subgroup of all scalar matrices with complex entries. It's the set of all matrices here that commute with everything. Okay, so what is Langlands-Tunnell? So here's kind of ordinary or kind of standard Langlands-Tunnell. We'll call it Theorem 2. Suppose rho from GQ to GL2 of C is odd, so determinant of complex conjugation is -1, irreducible and continuous as a representation. And suppose that when you look at its image in PGL2 of C, you get something solvable. Then rho is modular of weight 1. That's what Langlands-Tunnell says. That is, there's a new form, let's say G with Fourier coefficients B sub n of weight 1, such that BQ equals trace of rho of Frobenius at Q for almost all primes Q. Okay, so there's another version of Langlands-Tunnell, though, that we're going to want to look at, and it's maybe a better version in some sense, but we're going to have to see how they're connected. So again, that's another goal of this chapter. We'll call it Theorem 2, the automorphic version of Langlands-Tunnell. And it says the same thing, just in a different way, basically. It says, let rho from GQ to GL2 of C be an odd, irreducible, solvable representation. Then there is what we call an automorphic weight 1 cuspidal representation of GL2 on the Adels over Q, denoted pi of rho, of so-called central character det rho, such that the trace of T sub pi sub Q is equal to the trace of rho of Frobenius at Q for almost all primes Q. And I mean, there are a number of things that we'll have to define here. As the chapter goes on, we're going to have to define what we mean by automorphic weight 1 cuspidal. We'll have to define Adels, central character, and so on. But what is this T sub pi sub Q? We call that the Langlands class associated to the local component pi sub Q of pi of rho. Okay, this guy here, because this guy is a tensor product of local representations. So we'll talk about all that later. Okay, and so that's it for now. So we have a number of goals here. We would like to see how Theorem 2 and automorphic version and Theorem 2 standard version are related. We would like to see how the theorem from the proof of Fermat's last theorem follows from Langlands-Tunnell. We'd like to maybe prove or give a very good sketch of the proof of Langlands-Tunnell. There's a number of things we want to do here. There's a lot of terminology we have to cover and go over. Okay, so next time we'll start with a little bit of review. So thanks for watching, and I'll see you then.